Hello, Physics 30s. I want to cover, in this video, I'm going to cover the first two sections of Chapter 17. So that's detecting subatomic particles and the principle of antimatter. Okay, I'll break it up a little bit and then I'll do the other two in a separate video. So detecting subatomic particles has quite a history as well. As you can imagine, detecting things like electrons and protons um, was pretty difficult for those that were first studying the atom. Some techniques have emerged, though, that enable us to study particles that are smaller than the atom itself. So the first of them involved chambers. And the first physicist to actually study a way to detect these subatomic particles was Charles Wilson. You see his name listed down here, Wilson. And he was inspired actually by studying clouds. I'm just going to show you this here. This is a phenomenon. It's called the Brocken spectra, and it's German. Brocken is German. In fact, it's actually a mountain in Germany that was quite famous because lots of fog would roll into that area, and the fog would be below the mountain. So if you hiked up the mountain, you could see the fog below you, and when the sun gets behind you, it casts your shadow onto clouds, and that's what all of these pictures are kind of showing. I've never observed this. Actually, I have in an airplane. I've observed this, um, but if you're lucky and there's fog below you in the mountains, basically the sunlight is hitting the water droplets in the fog, and the light is being refracted and diffracted, and it's kind of backscattering back to your eye. And so and it's kind of cool because the shadows are um, really big, or they look really big because the shadow is on the cloud, and then you can sometimes see mountains past the cloud. So it's disproportionate. So it's kind of a cool phenomenon. But anyway, it'd been documented by lots of people, and it got Charles Wilson thinking about clouds. And he had this brilliant idea to actually create a chamber where um, there would be very dense or saturated water vapor. You can also do it with alcohol, as it says here. But basically, it became known as a cloud chamber with this super saturated vapor. It was right at the brink of turning into a liquid, right at the brink of condensing. And so it was a very unstable chamber in terms of the water vapor, but Wilson figured out really fast that if he fired charged particles into this um, saturated vapor, that it would trigger condensation. And what would happen is, and now these are pictures of them right here. You never see the particle because the particle is really, really tiny. But what's really cool is the particle will leave a vapor trail behind it, just like a jet flying overhead in the summertime or even in the winter. But you can see it a lot in the summer. If you look up, you can see this really long trail of white. And when I was a kid, I used to think that was the exhaust, and it kind of puzzled me because it didn't go away. But what has happened there is, the pressure, the circumstances are just right. I think there's a bit of pressure coming from the wing as it hits the air at that altitude. It condenses and it forms a cloud. Like it makes the water vapor in the air condense. Anyway, so the point is, when you look at these pictures, Wilson figured out really fast that charged particles would leave a vapor trail. So, if the charged particle went this way, then it leaves a trail of vapor. Like there'll be condensation right where the charged particle went, and you can take a picture of that. And if you apply a magnetic field, which was the next step that Wilson started doing, was you can get the charged particles will be pushed into a curve, okay? Because the magnetic field will push them into circular motion. And that set up a whole bunch of things because then you can tell, is it positive or negative? You can do some calculations. If you know the speed of the particle coming in, you can figure out its mass, just kind of like a mass spectrometer, but not in a vacuum though. Okay. So, and I'll touch on that point in a little bit. So, Wilson, actually, he was a student of J.J. Thomson. He was one of the students that got a Nobel Prize for this. So, anyway, the vapor trail is what causes the vapor trail shows the path of the particle. Now, pretty quickly after that, a number of other physicists realized that, hey, we could do the reverse. We could make a chamber that's actually a liquid and it's about to become a gas. And if we put that, it's just the reverse. But if we set up those circumstances, we can fire charged particles into that, and we can also observe trails. Now, but in this case, though, you're going to observe trails of gas, not trails of liquid. And so basically it became known as a bubble chamber. Okay. So you have basically a bubble chamber and you have a cloud chamber. Both of these chambers, and it's largely still how it's done today. It's a relatively straightforward way of creating a way to observe subatomic particles like electrons, protons, and then a bunch of other weird ones that we're going to get to shortly. Okay. So I kind of added both of those if it's helpful. A bubble chamber is really a liquid about to become a gas. Here's a nice picture of a hydrogen bubble chamber. You can do it with a number of different liquids, but liquid hydrogen, obviously you got to get it quite cold. But inside there, you can see these little bubble trails. Okay, well maybe you can't. This is kind of fuzzy, but introducing charged particles will leave tracks. Okay. Now here's a large scale one here, a picture here of a large scale cloud chamber. You see the workers there to scale. But yes, the way to analyze this is to apply the magnetic field. Now I should just know here. Here's another picture here. I'm focusing on this one on in white and black. This is showing a what happens or what can happen in a cloud chamber. We'll say this is a cloud chamber. It's a cloud or bubble, doesn't really matter. If a charged particle, okay, or no, sorry, in this case, a neutral particle was fired in like this. Okay, but remember, only charged particles leave trails. Okay. The neutral particles do not. Okay, neutral particles don't leave a trail. So what this is showing is that a neutral particle came in and then it collided with something. Okay, it might have collided with another particle and broken up into smaller particles. Okay, and then all of a sudden there were charged particles introduced into this chamber and they started to leave tracks. And notably, one charged particle went this way and another charged particle went this way. And you can see that there's a little plus sign there. But this is actually inside, or sorry, there is a magnetic field that's applied over this. And for our purposes, we could maybe draw it like this. So, we'll say that the magnetic field is into the page. Okay. Okay, so little X's here showing like the magnetic field's directed into the page. So guess what? This is where you have to use your third hand rule, and we're going to do this in just a second. But you can determine which one is positive and which one is negative. Okay, now something else though that you need to remember about chambers is they're not vacuum chambers. Okay, in a vacuum chamber, a charged particle would just be pushed into like basically a perfect circle, and it would just stay in a perfect circle if the magnetic field was strong enough. Okay, but that's not happening here because there's a whole bunch of there's matter in here. So initially the charged particle will start to go in a curve, but it's going to keep bumping in to whatever it's hydrogen gas or water or something. And so it's going to lose energy, like slow down, slow down, slow down, slow down, slow down. And that's why you see this kind of like cinnamon bun spiral, okay, in the track of the charged particle, because the particles lose energy. Okay, they lose energy and spiral in. I mean, you can add that if you want, but if that makes sense to you, okay. In these detection chambers, the particles are going to lose energy because of they're bumping into stuff. Okay. So those are the two things you need to know, and kind of just those general principles. Yes, you have to be prepared to use your third hand rule, which we're going to do in just a second. Now, This led really quickly, and actually it was already anticipated before cloud chambers were made. But um, a physicist named Paul Dirac, he predicted the presence, or he predicted the reality of something called antimatter. Now, antimatter is basically just matter, if you want. It's matter with opposite charge. Um, and it can be, if it's not, if matter doesn't already have a charge, then it can be basically understood as something with opposite spin. Okay. Now, spin is honestly for me, spin is a little vague still. That's a concept I've got to wrap my head around. But effectively, you can think of it as an object, like a subatomic particle. It could be spinning clockwise or it could be spinning counterclockwise. That's maybe as simple as I can and do for you at the moment. Um, so it means like a neutron. A neutron could be spinning in one direction. Okay, it could have its own spin, but an anti-neutron or antimatter, the antimatter equivalent of a neutron, would spin in the opposite direction. Okay, so that sounds kind of weird, but we've already kind of hit on antimatter. And what's really bizarre about antimatter is for every bit of matter that we can observe, the theory is that there's a form of that matter called antimatter. There's an opposite version of effectively every form of matter. Okay, now in 1932, Carl Anderson, he won a Nobel Prize for taking a photograph, this photograph right here. Okay, I think it's been flipped or inverted um, in terms of the contrast. But anyway, this photo right here, he took a picture of two particles that were in a cloud chamber. And very similar to what we just looked at up here, in fact, we're going to look at one in just a second, he saw two tracks. And in this cloud chamber, there was a magnetic field imposed over the chamber. And what it meant was, using your third hand rule, actually, let's say the particles were originally going this way, okay, in the which looks to make sense in terms of their curvature. But anyway, one particle went this way and the other particle went that way. And for to see particles moving in a curve in the opposite direction, if we used our third hand rule with your right hand, and let's say the magnetic field was into the board here, or into the page. I mean, it doesn't really matter. You could flip it around, but that would mean then that the particle that's going up, you'd use your thumb pointing to the right, and then your fingers would point into the page, and then your palm would push up. So that would mean that this particle was positive and this particle was negative. Okay, and Anderson just did some calculations and determined that both of those had the same mass as an electron, which it was like, what? How can an electron go up in this scenario? Because the magnetic field would push an electron down. So anyway, the point is that he discovered the positron. Okay, and a positron is an electron in every way except it's positive. Okay, so same mass, but positive charge. So I'll just walk you through this. We won't really do the math directly here because it's kind of been done for you. So here's another picture in a bubble chamber, this one. And it's very similar to what we just described, in that you don't see anything here until all of a sudden there's this part right here where there's a branch that goes on, okay? Where there's two tracks that branch away from that location. I think these little marks in here, I'll maybe get rid of that, but those are indicating a magnetic field, I believe, in or out. Okay, but the main thing here is that we see that initially, and I'll maybe clear that off because my drawing even obscures it. You see that initially the curvature is identical. Okay, and then you see this classic inward spiral, the cinnamon bun effect, because of because the charged particles are bumping into, in this case, hydrogen or something in the bubble chamber. Okay, so initially We do have a magnetic field. Oh, sorry. This question says that it's out of the page. Okay. There's a magnetic field out of the page. The initial radius of both of the spirals is 8.55 millimeters. Obviously, the spirals change over like as you keep going because the density of the liquid isn't uniform, and so you're not going to get perfectly symmetrical inward spirals. But initially, it is the same. It did give a velocity there. Looks like it's going at 0.0240 c. Okay, so that's a fraction of the speed of light. You know, c being the speed of light. Anyway, so um, it's explain using a sketch what you think is happening and determine the charge to mass ratio of both products and explain the significance of that. Okay, so here's a compression of what would happen. Again, the reason it's invisible, this first track, is because it's a neutral particle. So remember that neutral particles do not leave tracks in these chambers. They have to be charged in order to trigger the phase change. Okay, either condensation or evaporation. Okay, whichever one's going to happen. Now, but then you see tracks. Okay, so yeah, they're just saying here the radius in both of these cases is 8.55 millimeters. Using your third hand rule, the negative charge would have to be going up, and then the positive charge would have to be going down. Okay, so I'm trying to show you without twisting my wrist here. The correct third hand rule configurations. So to figure out the charge to mass ratio with all those numbers, we just do the same thing that you did with Thomson's apparatus. Okay, same thing. The magnetic field is causing centripetal force. The And in this case, because we could argue we don't know exactly what the charge is, and we don't know exactly what the mass is. All we're basing on, we're able to measure the velocity of the particles coming in. But then you get this. Now, this number, 1.77 times 10 to the 11th coulombs per kilogram, this is basically it's the charge to mass ratio for an electron. Okay. And for Anderson to come up with this, he's like, wow, well, both of these particles have the charge to mass ratio of an electron. Then they both have to have the same mass and the same charge, but the same amount of charge. But it's very clear that they have to have opposite charges. Okay. So this was kind of the first evidence of antimatter. Okay. And since then, there's been a lot of really useful applications of antimatter. But the quantum theory predicts that any time a piece of matter, okay, meets up with a piece of antimatter, okay, so they're identical in every way except they're oppositely charged or they have opposite spin if they're neutral. But if matter meets antimatter, when they touch, they annihilate is the term. And I kind of blew that up here. I added that. It says collisions between two will annihilate. And that means where all of 100% of the matter is converted into energy. There was a short video on that on antimatter, which is really fascinating. Okay, excuse me. So if a positron meets an electron, okay, that's what this is showing here, E negative and E positive. I know in simple terms, sometimes we just write an electron like E negative, and then we write a positron as E plus. Okay, and that may not be always the convention, but this here shows it kind of with nuclear notation, I guess we call it, where you have a 0, -1 and a 0, +1. Okay. But anyway, if a positron hits an electron, then they annihilate and they form two gamma photons. And those photons will basically move away from the electron-positron interaction. Okay, so you get these two electron and a positron, I guess like this. They come in and they touch, and then they completely turn into I'm having fun with Lego here. Photons, woohoo! And the photons move away. So anyway, the point is 100% of matter becomes energy. It's one of the most, it's a 100% conversion. And that process is called annihilation. In the video, if you watched it as well on what's called a PET scanner, this technology uses positrons that are introduced into the body and it uses the principle of annihilation to detect these gamma photons, okay, these two gamma photons that are produced when um, an electron and a positron meet. So basically, a patient, or here's what's really cool: you actually use um, I got that you use a radioactive isotope of some kind, and I had to look this up, but one of the most common ones is iodine 124. Okay, and you can just insert that into an IV. Okay, but and you can basically iodine 124 that's attached to a tracer protein or molecule of some kind that gets injected into your bloodstream. These proteins or these enzymes or sometimes they're sugars too. I think the video talked about a sugar. But anyway, they travel through the body and they're taken up by typically by tumors, okay? Like a cancerous tumor is a good example. Like it's overactive, it's uptaking sugar greater than the cells around it, the healthy cells around it, because it's like multiplying and stuff. So if there's an area in your body that is uptaking this tracer element with in a greater intensity than normal, then this iodine 124, all on its own, because it's not stable, it will undergo beta positive decay. It'll release positrons, okay? And when it does that, those positrons, obviously, they don't have to travel very far before they're going to hit an electron somewhere, okay? Because your body's full of electrons. So when that happens, you get this annihilation. And what's really cool is if they insert you in this circular detection chamber, and when that annihilation happens, one photon will go this way and another photon will go that way. They will go exactly in the opposite direction. Okay. Now, obviously, we're assuming here this patient's got a tumor in his brain or something. Okay. So this is where the iodine would be uptaken the most. And then, so yeah, like another one might, or like another pair of photons one might go this way and the other one would go in the opposite direction. That's the conservation of momentum at play. Okay. Like if one photon goes this way, then the other one goes in exactly the opposite direction. And a computer detects all of this and then just works backwards. So with a crazy degree of precision, the computer works backwards and is like, oh, this is where um, those annihilations are kind of pinpointing this specific region of the person's body. Okay, and then an image gets created, and a doctor with a huge amount of precision can know exactly where this tumor is. So, medical imaging is a fascinating kind of career field, and some of you may even get into it, like way beyond X-rays. There's a lot of ways: magnetic resonance imaging, MRIs, CT scans, PET scans, which is this one. There's a lot of ways to image the body, and sometimes you use the principle of antimatter, which is really cool. So you're going to use the annihilation of electrons and positrons. I'll just end this segment on symbols for antimatter. Um, like I did say, an electron is E negative for the most part, okay? But a positron conventionally is just shown as E plus, okay? Um, a proton. A proton is usually just written as a P, although sometimes I've seen it as P plus. Um, I have seen a convention that shows P minus as an anti-proton, okay? The truth is that a positron is really an anti-electron, but that name didn't catch on, at least at first. And so it became known as a positron. Okay. The others are a little less common, but they definitely exist and they have been created in the past. Um, the convention, though, that I've really seen, and if you look it up, instead of doing P negative, what all antimatter tends to do is just put a bar above the symbol. Okay, so an antiproton is actually written as a P with a bar above it. Now a neutrons are typically, I've written them as N0 just to remind me that it's a negative charge, but just a lowercase n is what is used to symbolize a neutron. And now an anti-neutron is just an N with a bar over it. Okay, so the pattern is consistent. Now, hey, you might remember this because we've studied it already. We came across a particle called a neutrino. Okay, in beta positive decay, you make a neutrino. Okay, it's an insanely small bit of matter, but they gave it the name of a neutrino. Now, if you make an antineutrino, this we have seen. It's a V with a bar over it, but that's what the bar is. Okay, the bar shows antimatter. So this guy's an anti or an antineutrino. Okay, so there you've kind of been exposed to antimatter already in some of the things we've discussed, but you'll see that in future applications here. In the next segment, we'll get into other bits of matter and their antimatter components. Okay, so anyway, that's good for now. You can I'll post the next one in the next section.